All right, welcome everyone to another OCP-TAP session, call number 112. This is a special session, so we'll hand it to Rodney to tell you more about it.
Yeah, sure. So this is, in addition to being an OCP-TAP call, it's also a joint meeting of the IEEE Industry Connection on timing in data centers. And I will explain what that is in a little bit. First, to kind of go over sort of the agenda of this meeting, like I said, I'm going to kind of talk about what this IEEE group is. And then after that, half hour or so, Ahmad is going to present some slides that he's done previously on some use cases for Metis applications. But before we do that, I will begin with this single slide to go through some of the policy stuff. So when you clicked agree to enter the meeting, you agreed to be recorded, like OCP-TAP calls have typically done. For the IEEE side, if you've participated in past IEEE meetings, you're probably not used to that. Generally, IEEE has not recorded meetings and has had policies against doing that, actually. Apologies for this meeting being kind of delayed. One of the reasons it was delayed was that we actually, Ahmad and I sort of convinced IEEE to slightly change their policies and allow an industry connection, which is what this is, when it's doing presentations, so not making decisions or anything like that, to record the meetings. So this is a joint meeting of OCP-TAP and the IEEE Industry Connection Group. The meeting is recorded and will be posted to YouTube later on with a link. In addition, IEEE needed to add these extra disclaimers and policies and so on. So when you click agree to enter this meeting, in addition to accepting the OCP policies, you're also agreeing to accept the policies for this IEEE group, which are linked here on this site. And you can download this, by the way, with what I showed you previously. You agree to the IEEE privacy policy and you agree to IEEE events and terms and conditions. So I needed to kind of present this as part of the joint organizer work, just to kind of get past that. So from that, I'll kind of move on to the next topic, which is, what is this thing that we're in? So the industry connection sort of, I guess, organization within IEEE is kind of designed for what most people would call pre-standard work. And what I mean by that, in other words, is something maybe isn't fully understood or fully known in terms of like standards that could be done. Obviously, IEEE standards are the the focus, but it could be other things, an IETF or ITUT, you name it. So kind of the idea of this industry connection thing is to do, like it says, basically connect one set of experts, in this case, timing experts, with another set of experts. And in this case, that would be operators of large data centers. And basically discuss use cases and requirements. So in other words, not really discuss formal standards work of like, you shall do this, you shall do that, but more what's needed, out there, and how can that influence standards. I'll give an example a little bit later of one thing that's come up, but that's kind of the idea of this group, is essentially with respect to data centers and with respect to timing, to try to focus on use cases, meaning how do data centers use time, and requirements, meaning how would a data center want to distribute time throughout the data center, maybe even between data centers. So that's kind of what this group is about. When we say that it's a joint with OCP-TAP, so obviously not everything that OCP-TAP covers is in this category. Those calls will continue and will be run the same way they've been run in the past. Whenever we have a presentation that is in this kind of category, basically use cases and requirements for data centers, we're planning to have that as a joint meeting with the IEEE group and with OCP-TAP. And we're using OCP-TAP's call infrastructure, as you've seen. So that's pretty much what the group is about at a high level. I have some kind of things that I threw in here that we can always change, but so what are some examples of use cases and requirements? I kind of listed here, kind of generically still, performance, software applications, Energy savings maybe is another one that has come up. Requirements could be, I need this performance. Do I need frequency? Do I need time of day? Am I using Ethernet or some other method? And so on. I'll give you an example that came up recently, not to like fully discuss this topic or anything, but just to give an example of something that's come up recently. So in 1588.1, the IEEE standard that has just started on client server PTP, it's kind of become somewhat obvious that that particular project in IEEE is focused on using PTP in unicast mode. In other words, if you weren't using unicast, you wouldn't necessarily need 1588.1. That was kind of what was discussed recently. So if someone asked, for example, well, of all the different data centers out there that want to use PTP, you know, and again, that's maybe a subset, you know, who knows? Are they all determined that they want to use unicast, or are they open to using multicast PTP? And the general kind of sense of the call was, we know there are some, in particular Meta, that insist on using unicast. We know that for sure. Beyond that, we're not so sure. So like someone in the call even suggested, maybe that could be some topic that we discuss at some point in this group. You know, basically just the general question, do data centers need unicast when they're using PTP? Again, everybody may say, well, maybe that's obvious, you know, we don't know, but it's an example of the kind of thing that would be helpful to know. And knowing that would then in turn help the IEEE work that's going on now. So that's like an example of something. Who is most desired as a presenter? Nobody is excluded, obviously, and this is not intended to exclude anybody. But what we're really trying to get is as much as possible, get feedback from large data center operators, let's say hyperscalers is a general word. To give you another example, I work at Keysight. Keysight sells a lot of test equipment to data center operators. I could give a presentation saying, well, from Keysight's experience, we think people want this and people want that. But then you could argue, well, but who is Keysight to say that, right? That's secondhand information. It's not as good as actually hearing from the companies that are actually deploying this hardware and setting up these systems and so on. So I could give a presentation, but that wouldn't be the ideal, I guess is my point. And again, that's not to say that anything isn't welcome. Obviously, anybody that has opinions on things is more than welcome. And again, some of the standards, IEEE 1588, 1588.1, the new standard that's going on, but also other things, NTP, GNSS, 1PPS, anything that somebody could come up with to distribute time throughout a data center. ITU standards as well are certainly an important topic there. So that's kind of the what. I'll stop, by the way, before we go to Ahmad's to go through questions. Presentations, they're held as Zoom calls. The meetings and events that I showed earlier, the tab up there shows the upcoming calls. No membership of any kind is required to attend a presentation. So you don't have to formally join this group in order to watch these presentations. If you are interested in giving a presentation, please contact me or Ahmad, basically at the emails here, and let us know. If you have given a presentation in the past at, say, a conference, and that presentation isn't really publicly available, feel free to repeat it in this event. That is also more than welcome. Repetition is fine. In terms of all the formalities of how it's organized, so we started this off in the IEEE Industry Connection program. Basically, there were a handful of people that filled out the forms and the paperwork to get it started. There's an activity initiation document, if you're interested, that is basically the document that kicked off the group. That also has some of a link to the formal policies and procedures. We use what's called an abridged policies and procedures for this industry connection, and that word abridged is what it says. It's intended to be as short and simple as we can make it. It's only about 2 pages, but feel free to go and read it. TAP has been tracking this goal, basically what I described above, for many, many years now. That's why we thought it was kind of obvious to just do it as a joint project. And the Industry Connection will operate jointly with OCP-TAP. So yeah, they're held as Zoom calls. They're recorded on YouTube, and you're notified of that, obviously. We'll keep agendas and minutes in the agenda and minutes thing up above. What this paragraph is basically saying is we're going to try to be as light as possible on the minutes and stuff. The minutes are generally going to be someone gave this presentation and it was discussed. We're not going to record everything that everybody says or anything like that. And then here is getting to kind of the formality part of it. So in IEEE's Industry Connection program, the assumption is at some point in time, we'll have a whole bunch of presentations where different people will give their opinions and feedback and use cases and so on. And then ideally, the group will write a white paper. And you could think of the white paper as just an attempt to try to summarize everything that we've seen in presentations and so on. Creation of that white paper and like voting on it and stuff is a little bit more formal process. So there's an IEEE workspace called iMeet that we will use in the future to kind of work on that white paper. So the white paper initially, when it's being drafted, will be out of the public eye, but it'll be accessible by members. And then if there's a controversy of some sort in the white paper, we will vote on what to do with it and everything. Many times voting never happens from what I've heard in these Industry Connection things. But like I said, if there's a controversy, we might need to vote. And because we might need to vote, there's more bookkeeping on who's a member, who's not a member. So in order to, that'll happen in the future. Today, I would say you don't need to worry about it too much. But if you're interested in joining that, the abridged rules that we have are essentially you fill out this online form here under participation form. You say your name, what company you're affiliated with, and so on. And then that's it. You're a member. We don't plan to have attendance requirements or anything like that. Like I said, at the moment, we're not even really planning to use that. It's going to be just presentations and so on. But nevertheless, if you're interested in becoming a formal member, please do. Please fill out the form. And that's that. We do have some mailing list. There's an email that if you send to this, it'll go out to all members. Basically, everybody that filled out that form will be on the mailing list for this members thing. And if you want to contact Ahmad and I, you can send to this email. So one other thing to mention before we go on is there is an ITU Study Group 15 Question 13 group with kind of a similar agenda, actually, trying to explore requirements and so on for data centers. That's because ITU could or would or might have standards down the road for this topic. So they're trying to gather feedback as well. At the moment, this is a separate set of calls that aren't really being held jointly with this set of calls. Ahmad and I have offered for a merger, basically for ITU to kind of join as a third partner in this call. That's kind of a work in progress, hasn't really happened yet. So for the time being, there's two separate sets of calls. If you go to this link and look at the recent minutes, it has a list of the upcoming meetings in 2024 and how to log into those. So that's kind of the current state of things. At this point, I'll open it up for questions if anybody has anything to ask. All right.
So the meetings itself will be on Mondays or on the regular OCP-TAP timing? Good
question. Ahmad, feel free to chime in, but what we were thinking is that the time will be the regular OCP time, which is made to be convenient for folks in US Pacific and US in general. Our thinking is that obviously there's other time zones and it's inconvenient for some people, but it's recorded. So everybody can kind of watch it. In terms of the day, we wanted to kind of keep it, we're assuming that this one may gear up and start happening every 2 weeks. So we didn't want to collide with the regular time for OCP-TAP, and so that's why we put it on Monday. I don't know, Ahmad, any?
Yeah, like basically, Zoli, it will be just the regular OCP calls, but like it will be basically in the beginning of it brought to you by IEEE IC.
Yeah.
So like, and then when it's also announced, you see that as well. Again, we don't want to bloat things. We want to show like that we're basically opening some like focus groups, you know, like, okay, these like, let's say presentations are focused this. If someone is watching all of them, going through all of it, you get all of it. But like, if someone wants to be just specifically looking for those things, then you can watch out for those. The thing is, like, as you're familiar with OCP-TAP, like we go through a very broad, like, let's say, spectrum of things, like from atomic clocks all the way to, let's say, the GNSS. I mean, of course, they're all related. They're all part of the whole supply chain. But let's say this one will be specifically for applications, like application for precise time in data centers.
Yeah.
I hope that.
Well said. Yep.
Yeah. We have Hank.
Hey.
So Rod, I have a question.
Wait, Hisham, Hank is asking a question first.
Can I ask the question or not?
No, wait. Hank is asking first.
If you can let Hank go first and then you, if
Yes.
that's okay. Yeah.
Okay. So are we discussing the need for time in the data centers? You know, do we have the right people for that? For example, I saw that Amazon Aurora, you know, database keeps a log of all the transactions, sorts them by time. This is a big charted, distributed, replicated database. It pulls all the logs together, sorts them by time. You know, and that's why time is important, because at 1 millisecond, you've got 500, well, assuming 1 millisecond before or after, you got 500 different time buckets.
Yes.
At 1 microsecond,
Right.
you've got a lot more.
Yeah.
So
Yeah.
So the answer is like anything is welcome. And again, sorry, Hank, since you've been like part of OCP-TAP for many years, feel free, like, you know, suggest people, invite people, let us know what we can do. This is
right.
work.
Yeah.
that's the problem. I don't know what I don't know, and a lot of the people in the data centers may be on the, you know, the networking side of the data center, down in the physical aspect, where what they want to talk about is the upper level, the databases and AI. How does all that use time?
Yeah.
Right.
We don't know it, and without knowing it, we can't have a really intelligent discussion.
I agree with you, Hank. Like we've been heavily focused on the how rather than the why for many years. And again, it's part of the chicken and egg, right? Like, but now we are at a point that the how is, I mean, to a certain extent, like how is more heavier than the why. So now we want to put more emphasis on why. And this industry connection is pretty much geared toward that.
Absolutely. I think the short answer, Hank, is yes. I mean, that's basically what we mean by use cases, you know, including all the way up to AI, distributed databases, you know, you name it. And in particular, I mean, just to call out Amazon a little bit, Amazon actually did a great presentation at the WSTS conference on some of their needs. Repeating that in this would be awesome. I don't know if Josh or any of those guys are out there and hear this, but, you know, simply repeating that WSTS presentation even would be awesome, you know, because it talked about some of those things.
Well, you know, even if they repeat it, it's going to be updated. They're going to have thought about it twice, I think. So it'll be even better than just watching a recording.
Exactly. Yep.
And plus, it will be available to public on YouTube. Everyone can see it forever.
Yeah.
Yep.
All right, let's give the mic to Hisham. Hisham.
Yeah, sorry, Ahmed, I'm just walking to my meetings. Anyway, I just parked my car, walking to my meeting. The question I have, what do you plan to, if you, given my experience in ICs, usually they aim for, aim to standardize something. So if this is the case, then what do you plan to standardize in this effort?
That's a really good question, Hisham. So there's kind of a mix going on now. So 1588.1 is kind of going on now, and it's intended to help data centers, and be used in data centers, right? So like that example that I gave earlier, there's kind of some active questions that are coming out of that work, and that might come out in the future. Beyond that, I would say beyond 1588.1, it gets back to what Hank said earlier. We don't know. We don't know the answer to that question. Like, in other words, maybe we will go through this and we'll discover that a new standard is needed. Who knows? But we don't even know that, I would say, yet. So I can't answer it because I literally don't know. It gets back to what Hank said earlier, that we kind of need to discuss some of the why more, maybe, and then make a decision like, are the current standards good enough? Maybe they are. Do we need something new? Maybe so. We'll learn as we go along. Like Ahmad said, we're trying to keep as an open mind as we can on it.
Very good. Thank you. Thank you.
You're welcome. Any more questions from the audience?
Yep. All right. If not, Ahmad, if you can take the share, feel free to go through your
So here is
presentation.
so this presentation is basically an example of, let's say, repeating. So like I basically presented this in another one of these conferences, and I thought like it would be just a good teaser, like basically to just kick off these things, because the focus is mainly on like data centers, and by no means this is the answer. This is more a framework and basically more questions. So, and again, it's been a year and a half. I mean, I presented a year and a half ago, so I literally did not want to like prepare for it or anything. So I'm going to improvise in real time in front of you. So, so that means like I might not have it like perfect or whatever, which is fine. So the whole, let's say, motivation of this, like this topic, this presentation came from, I mean, it came definitely from my internal, like, interest in this topic, but this was something that was striking for me. A webinar was set by Setentrio in 2023, I think, somewhere in 2023. And it struck me to see like data center, it was basically, there was a survey in it, applications for precise time. And like, I mean, aside from that was also like the need for anti-jamming and spoofing protection. And it was like a survey ran there, and data center scores the lowest. So this was basically telling me somehow that, I mean, from the audience, I mean, you can also assume like most of the audience were perhaps on defense and power grid. That's why those score the highest. But in general, there is a lot of misunderstanding and misconcepts, or like some, what do you call, just some idea. Like someone, for example, reached out to me, asked me, what do you think about this hypothesis of precision, precise time or precision time synchronization improves the performance of servers in a data center? And I'm like, you gotta open this a little bit more. Like, first of all, like, improve what? Performance, I mean, that's very subjective. Which part of it? On what application? To what extent? And like, I mean, that was like that specific question came from someone interested in, let's say, assume like some high-end atomic clocks or optical clocks, and they wanted to see like if there is a relevance. And again, I don't want to spoil what I have upcoming in this next month, like of presentations. I have a presentation that actually talks about the roadmap of how you should actually equip your data center with precise time. And I start also with a lot of critical questions of like, can you get a value proposition before like going further with this? What are the, you know, like the potential applications you can get there, how you want to find the bridging and like the, like all the, like bridging the gaps, and like some more, you know, things which I break it in phases. Again, I don't want to spoil that presentation, but that will be, let's say, in a month coming soon. One thing I wanted to elude before we go further in the presentation, this is a slide from the first TAP call 4.5 years ago, which you can see like we were aiming in the vision of what we had for TAP, basically IEEE and ITU, and Datacom, basically us. And we want to have basically OCP-TAP somewhere in between. So this is not something that we just thought about it. And here's a solid proof. Like we've been thinking about this. We never wanted to be a separate thing. We just wanted to be basically in the middle, trying to add our value to whatever we can and basically cover up for things that are, let's say, blind spots for these other organizations. So the presentation I gave, but like into a year and a half ago, like I started or a year ago, yeah, like was basically it's like this track that I always like, the or biomorphic approach, where you look at like, you know, or like, you know, like biological or, you know, living things, and you try to get some inspiration how things work. And this was triggered actually by a talk we had on OCP-TAP. You can go find it, talk number 74, which was about the brain's clock and like basically how like the entire, like, you know, distributed system of cells in our body synchronizes and how it uses and so on. And then it was basically going through how those cells evolved from basically first figuring out the presence of the sun, and those who didn't, and then the one that they were not able to detect the sun basically perished because of the UV exposure. And then the cells that were able to detect the sun, they figured out that there's a cyclic thing with the sun, comes and goes and comes and goes. And they're like, okay, let's get some timing so we can go before the sun comes up, or like right after the sun is gone or something, so we can get more food, or again, minimize the exposure of UV. You know, it's like you get the UV, but then it's too late. So then there was, again, some advantage in those. And then that was basically the first form of synchronization. That's like how cells developed this cyclic tracking, basically the like time. And then further down the road, some more cells figured out that like, oh, the cycles from the sun, they go through some adjustments throughout the year, and they figured out like basically the synchronization, where like they can now change the frequency as they go through from like basically from summer to winter and so on. So I thought like this is very interesting, because you will see like in the presentation, a lot of these topics will show up. So this is just quickly like showing the relationship between frequency and the duration. Like basically the frequency integral of the frequency gives you a duration, and a constant, which is basically, that's like your accuracy, where, I mean, the frequency also has the accuracy component. Where do you start from? And then we discussed the fact that when you have, let's say, synchronization, you have this thing we call pseudo entanglement. Basically, how you have in quantum physics, like, let's say, the entanglement between two particles, and let's say there's always a complement spin between two particles that are entangled. You can have the computational version of it with the presence of clock. When an event happens simultaneously over and triggers a timestamp on two separate clocks that are synchronized, you're going to capture the same time within, of course, the window of uncertainty. Again, that's a statistical thing. And now what can you use this for? So we broke it into 4 pieces. And it's basically a permutation of frequency versus phase with being active or reactive. And by active is you do something with it, and reactive is it happens, you just take a timestamp and you take a read with it. So for example, let's say if you take timestamp from a clock, that is just a reactive thing. But if you have a ISR that triggers on a certain alarm, like basically on a certain time, and it executes on a certain time, that's an active. And now we can do the same thing for frequency. For frequency, it will be more like you have a succession of events, you compare it with the frequency that you have as a source, and you say like, you're so much off, versus you take the frequency that comes in and you apply everything through it. And let's say that will be the distribution of your clock. So with that in mind, we broke this to a bunch of examples. And again, this approach is like, okay, you're in a certain industry with like certain customers, certain applications and so on. And it's always hard to figure out, okay, we want a precise time. Where are we going to apply it? It's much easier if you break the problem, divide and conquer, with like, how can I, let's say, utilize, let's say this class 1, a synchronization, an active approach, you know, or like, how can I use the synchronization and reactive for something? So I just have a bunch of examples here for you guys. And I hope you just take the structure for it and then you go further. And then I think all of us can agree, anything you come up with, let's say for a data center in the future, you know, like with applications, should fall in one of these 4. Like you cannot really go out of this. It's like, that captures everything. Either you deal with a frequency or phase, you do it active or reactive. It's nothing else. So now, I mean, I gave here a little bit of a example of, let's say, how these LLMs are growing. And like, I mean, you can see it's 2022, but now 2024, we have definitely more updated things. As I said, I didn't want to touch the slides. Just wanted to keep them as is, just go quickly through it because I thought it just can be a good hint or just a Kickstarter. And like, you know, here you can watch like the growth of like these LLMs. And basically, this is something that is very interesting, let's say, when it comes to combinatory circuits, which, let's say, back from digital logic, you have combinatory circuit. You have, of course, you have first the combinatory, but then you have the sequential circuits. So the sequentials, they start basically with the introduction of a flip-flop. And here on the left, top left, I have a finite state machine, FSM, which is like used, let's say, to show like these machines going between different states based on an input, providing a certain output. And this can be expanded to a lot of, let's say, things. And again, a lot of these FSMs are like the key components, basically, in your processors and like in hardware or whatever you deal with. So a analog version of this, like in time domain, is basically the state space representation, which you have basically 2 equations. One equation is the transition equation, which you can see here. It basically shows you the x dot. And y is basically the one that is just the output from that inner state that is happening. A statistical version of this finite state machine, where the transitions are not just based on input, crisp based on an input, they're based on statistics, is our very famous Markov chain. And now, last but not least, you have this thing called the state transition matrix, which is also stochastics, which is much bigger, that takes basically an input and then spits out another output. Is pretty much the foundation for all these LLMs. I mean, this is really an oversimplification. Like this is more like for recursive neural networks, and then you can add to it, like, you know, these different mechanisms like attention, and then like just build it up all the way to have like what you have the LLMs. So basically, there is always an input. Of course, with a mechanism, in the transformers, you have the attention, like that is increase, giving you like also a relationship between every word. We don't want to get to that details. Just want to, there is a reason why I'm showing this. And just for a time being now, consider like this, like the state transition matrix. It can be also similar. It can be somehow referred to the embedding table. And these are very large because you have basically tokens on, let's say, on both sides, like on horizontal and diagonal. And you can assume like these are in billions, if not bigger, like in size of matrix. Of course, like again, this is really oversimplification. I'm trying to just tell you like there's a lot of parallel work that has to go in, let's say, in AI, and how perhaps when you break it in a distributed system and you have things working in parallel, how this can come handy. So now, some of these operations, they differ in power consumption as you go through them. Like there is a lot of parallelism, but then due to again how math works, like let's say when you want to add things, you're basically you're going through an operation called all reduced. So from all of them, you get back to, let's say, one. So you have different power profiles for the operation. That different power profile can create spikes. And the spike is basically, it can be a trough actually, or a spike. And as you scale these models more and more, you can have, you will have basically more of scarcity for power. You reach a point, let's say, where the power determines how much you can cram in hardware to run certain things. I mean, you're following the news. Like now we're looking at like, oh, putting these data centers right where the power generation systems are, is looking into nuclear, looking like there is so many like, you know, things that are like, you know, getting reshaped because of all this power. And of course, the number of machines, as the number of machines keeps increasing, you have more heterogeneity. And like traditionally, like let's say we were just profiling the power for like entire data center based on the peak and also some, let's say, safety margins. But when you are really expanding so fast, you cannot just have safety margins. You start like going through safety margins, getting them off, but then you start looking like, can I do something, you know, instead of peak, aim for average, you know, like, and then this is where you want to really reduce peak to average. And it would be great if you have, let's say, these spikes not falling on top of each other. But again, as you approach all these different, you know, schemas and try to solve something, then you break something else, you know, like then you have like tail latency. But then if you solve the tail latency and you have the spike, then how about the network? So this just keeps going on and on. Again, I don't have answers for these things. I'm just trying to like bring up like, again, more of this problem. So this is another one. And that's like, again, the tail latency, as I like brought up, like you have heterogeneity. Like you have again, if you're in semiconductors, in production, you know about semiconductor production and so on. I mean, if you deal with real world, you always know homogeneity is just an assumption. It's an asymptotic thing. Everything is heterogeneous. Everything is different. Everything is made by like different purity, different, like, yeah, we put them through buckets. Like, I don't know if you know, like, for example, you buy different CPUs and they come in different speeds. Did you ever wonder why, like, these companies actually make the CPUs with, let's say, lower speed? Well, guess what? They don't. They always make them with the highest speed, but when they go through manufacturing, they go through a process that is called binning. And they basically take them through this binning, and let's say the first ones that they fail, I mean, there's a certain limit. If they fail, they're scrap. Then the first one they fail, they become, let's say, the low end. Then they keep cranking up the survivors. And then some fail, they become, let's say, mid-range, keep cranking up. Again, the one that they fail, they become, let's say, the high end. And then the one on top, let's say, go for some research or something and so on. So that bucket is not narrow to one parameter. That bucket is wide. Even if you get the same processor, this can be a GPU, it can be a CPU, you have heterogeneity. And this heterogeneity just gets worse as you scale. These are those problems as when you scale, things get worse. So you can introduce some concepts like, for example, overclocking, micro overclocking, but you don't want to overclock everything because you just augment the problem at, again, and then you hit the power, you have all these problems. Or if overclocking is not an option, you can underclock. Actually, you don't have to consume so much power, let's say on the one that goes so fast and has to stay like this waiting for the slowest one when you're bounded by the slowest one. So for example, in operation, I mean, all of these MPI operations like all to all reduce, all of this, you're bounded always by the slowest. So what if you can actually use this precise time to bring the alignment and again, crank up or crank down, and you make things pretty much work like together. Another one is like in RAS, where you're like looking for a like an event, association of events, and you're trying to find out like when something started and caused like a cascade that just breaks through everything. So if you look at like just today's, time stamping that we have, let's say with provided by Linux kernel, like dmessage. Dmessage, first of all, runs based on boot time, means they turn on like the CPU, TSC starts counting from 0 and you just go through. So boot time, or I mean, the clock that is used is called clock underline raw. And you can synchronize that clock. It becomes clock underline raw underline monotone. And then you can apply synchronize. You apply just the C, basically a start to it. And now you can turn it to clock underline real time. dmessage doesn't use it. As I said, dmessage uses just clock underline raw. So now they're different scales. Machines, they don't start together. And if even they start together, reset comes up, they're not synchronized. And like again, heterogeneity everywhere. The oscillators that are used, they are heterogeneous. There's always some ppm difference between it. Hopefully ppb, we just get it. But still, like you're basically on a holdover with all of them, even if you were starting everything together. So an event that happened at a certain time in machine A is very hard to associate with, it's impossible to associate with machine B, with machine C, and find out like reconstruct this, let's say the order of events. So that is where precise time can come in. Precise time can come in and then brings for you basically an alignment of these timescales. So now these timescales can get translated, or like you can, let's say, have them all in clock under real time. That is backed by a nice backbone of, let's say, PTP and PTM. And now you know exactly when things happen with regards to each other. And then from there, you can, let's say, trace back if an event happens, when was the first thing that happened. And we also push this a little bit further. We actually developed something, you can find it on GitHub, called Tango. It's like a piece of software that runs, it's really in infancy. We open source to put the whole thing on the Timecards GitHub. If anyone wants to continue on that, or you want to discuss, feel free, like reach out to us and we can see what we can do. The other one is like network congestion. Now, when you aligned everything, you brought the homogeneity. Now you want to throw things off. Well, what will happen with the network? If you have everything aligned, you will definitely cause congestion. You're basically throwing everything in the network and say, good luck with those deep buffers, that the buffers figure things out. Problem with buffers are they're like tax. You pay time to write in them, and you have to pay time also to take from them. So why not get rid of them? Okay, how you want to get rid of them is if you have some determinism in your network. Again, we're not saying you want to completely get rid of them. You will have still buffers because, again, heterogeneity is everywhere, and you want to have always some flexibility in your system. Even time, this whole like operation of like time synchronization is definitely not a hard rock things like they will always work. Like you always have, again, it's a statistical thing. You have servos like always jiggling between an error. You have some window of uncertainty. So you can minimize the buffers, or if you can afford them, you keep them as the same size, but you don't use them. You use them only when it's needed. Similar to the bumper in your car. Your bumper in your car is not meant so you go with your car and just bump in every other car in the traffic. No, it's there when, you know, in a rainy day, when like your car slips, something goes out of control, it minimizes damage. So it has to be just there as a damage control rather than like something you constantly are using. And basically you want to have like the divergence basically of the flow to be zero. So you don't just account for what you basically transmit responsibly. You know, like when you put data there, you know, the pathway is ready for it. But how can you do that in a system with a lot of agents? That is basically a question to solve. And we think any solution that comes definitely needs precise time for it. And of course, now all of these that I explained, they were more in the physical realm, like basically they are things like network, power, the heterogeneity. These are all physical things. There are things that are logical. And logical is like, again, in data, for example, the thing with the consensus in this distributed systems. I mean, we know Paxos, great method with 3 phases to get like consensus across like shards and across basically multi-agent containers, both in read and write. And you want to have always like, let's say, an option to choose between availability and consistency. And we see like precise time can actually play a key role there. Like, I mean, with the introduction of this method called commit and wait protocol, you can perhaps get some gains by reducing, let's say, the clock skewness all the way to the latency, which again, you get bounded by another theory called the Cal theory. We have a call, don't have it on top of my mind. You can find it by Professor Edward Lee. He goes in depth through that. And you can see like, let's say all the way, let's say the latency in the system, the lowest latency in the system, let's say in data centers, is somewhere single digit, let's say microseconds. In the absence of precise time, if you want to just use, let's say, NTP, you cannot really guarantee those numbers. And let's say with PTP, of course, yeah, you can say, oh, who needs like, I don't know, nanoseconds? Well, if you want microseconds, NTP is not going to give it to you. So, but PTP that goes in, let's say, nanoseconds can provide you the microsecond. So perhaps that can be something you want to consider. And again, this is also the landscape of things. Like we've been working with the community on the time card on IEEE P3335. That is basically when you don't have a network, when you are in WAN, you want to bring to your data center time. From there, you have like PTP. You can go, if you don't have, let's say, hardware timestamping in your system, you go with, let's say, a network of TPS. You can go, let's say, if you don't need that, like, I don't know, the video industry or something, they use IRIG-B. You can use White Rabbit if you really need like so much, you know, precision, much higher than what PTP can offer you. And of course, you see like on top, again, Rodney, this slide was before, was prepared before 1588.1 was there. I would have definitely.
That's fine. things change fast.
Maybe I can just, for the record, add it here. And just add it here.
Don't worry about it.
1588.1. Oh, it's white. So where can I? Here you go. There you go. So, and then last but not least, you get the precise time to your NICs. But then now in a system, you need to go through the PCIe bus and like get basically to the processor. That is where basically we have PTM and this new work from my colleague Julian and some more folks here on PFM. And of course, like it's very important to look at not trying to kill a mosquito with a hammer. So you look at like, where are you really like in terms of applications? Maybe you're fine. You don't need any of these things. Maybe you just have a co-location of a lot of machines serving customers and different things. And there is not that much shared commodity, which I doubt. There is always some shared commodity. If there is none, then you don't need to worry about any of this. But if they are, you look at like how far you have to go in this chain, and then based on that, you make the right decisions. And with no further ado, this is the conclusion. Let's go for questions. Rodney, back to you.
All right, great. Yeah, opening the floor for questions. I guess, Amada, if you could go back to the slide you had earlier with the performance numbers on it.
Sure.
Something that kind of occurred to me after watching the second round of this presentation, that like you said there, this is kind of getting to the question of, well, what performance do data centers require, right? And it kind of occurs to me that in some other applications, like say 5G front haul or some of the telecommunications applications, again, maybe I'm misstating this, but they tend to have one application, like one use case. Like, for example, in front haul, there's multiple radio scheduling packets, and you need to get that schedule aligned. And so you need PTP.
Yep.
And because the radio has a lot of known requirements from 3GPP and so on, they know the number they need in this kind of scale. Like, we know we need whatever it might be, 5 nanoseconds or something like that, because they kind of have one use of it. What's jumping out to me with these slides is in data centers, there's multiple potential uses of time, right? The power saving thing, associating events, distributed databases, and so on. And sort of my takeaway from this slide is once if you have multiple things that you're using time for, it's kind of hard to come up with, here's the one and only number that I need, right? The short answer is I need as good as you can give me practically. Is that sort of the message of this slide? Am I getting that right?
So basically, the key thing here to consider is you can always use something that has higher precision for lower precision. So now going back to the applications, yes, most of these applications, there are certain bounds. For example, let's say with the databases and the logical ones, again, they live in the presence of the network latency. So the same thing applies, let's say, to this 5G applications and something. Why 5G application needs to go in nanoseconds so deep? Because it deals directly with speed of light, and your customers are on the bottom of this chain of, like, the network.
Right.
Well, this in a data center, your customers are on top, going via the networks. The servers, they're just sitting on the bottom, and they serve everything via the network. Things that they go with, a scale of speed of light is, let's say, for example, a spike in power going through, like, your system. Network congestion, perhaps, again, it's much slower because, again, it's also kind of a logical thing, let's be honest. But I mean,
Right.
the traffic going through things, and you don't have that much the spontaneity because, like, these nodes, they already received like what they should do, and they provide it back. While in the 5G and the cellular and like in telecom, customers are, again, you serve the customers from the bottom of this tentacle.
Right.
So that brings like those differences, And now another thing that's very important to understand is a lot of these applications that we bring up, because of, again, these Cal theory and everything, you can benefit a lot from precise time in a data center itself. You can be fine if you only have one data center, or you have multiple data centers, but every data center is doing the operation independently, not doing things together. They can go as a raft together. So you can care less about, let's say, I don't know, GPS gets jammed or something, whatever. Like, you're still here, you do your operations, and let's say a rubidium clock can give you what you want for a foreseeable time, and anything more than that in terms of outage of GPS is hard to imagine to have, let's say, I don't know, more than 24 hours. Well, you might be in a war or something, like you have like bigger problems to deal with, So,
Right.
I mean, again, we have to be also very cognizant on that. Is this data center for what? For, let's say, social media? Or is it for, let's say, some high-end government something? Well, then you treat it differently, So that's why I'm saying it's very important. You look at, like, what are you trying to solve? What are the applications? What are the needs? And then you break it through the solutions based on what you have on hand. Hank, you want to say something?
I've got a few things, and you just added a couple, Ahmed.
Yes.
One is I'd like to point out there's a difference between precision and accuracy.
Yes, I
If
didn't
you
know
look
that.
online, right, and I'm glad you guys are using precision, because accuracy is across data centers. Precision can be within one data center. So you had mentioned something about that recently.
Yeah.
Now the other thing is about one thing we're not putting in here is cost. I'll ask customers, well, what kind of accuracy do you need? And I'll say, femtosecond. No, wait a minute, attosecond.
Exactly.
Okay, it's going to cost this much, and it's going to involve a huge research project. And all of a sudden, well, 100 microseconds isn't so bad. So that we have to be cognizant of the cost.
Absolutely.
As you said, the military maybe has a bigger cost. Maybe somebody only really needs to be good enough for Kerberos. 5 minutes. So there's a huge range in there. And the other thing is, what kind of data centers are we talking about? Because there's a difference between a cloud data center where everybody's sharing networks, and multicast has a problem with security. You don't want to have everybody else's multicast hitting your server, and you don't want your data going to their server, as opposed to a private data center where you own everything in there. Your guys can go down, put in a protocol analyzer and see what's going on each connection. And then in the middle, there's the data centers where you can go and put your equipment. It's almost like having your own data center, but not quite. So those all have different needs for accuracy. And again, with time, there is a security concern too. Ahmed, one last thing is, you said if you're in a war zone, well, there's some maps of where GPS is being jammed. And if you think about the western border of Russia going down to the Middle East, it's pretty much constant jamming in that area.
No, fair. Yeah. Like, I mean,
good points.
If someone wants to operate somewhere, like, in an environment hostile to GPS, so I mean, you have to really look for some alternatives if you're dependent on time. And I guess there are a lot of solutions available for that. I mean, they come with cost. So I mean, you have to understand, like, if you want to go and race in Formula One, you have to have something that's a Formula One thing. You cannot just say, well, I'm taking my car and then, well, good luck.
That's a good analogy, but everything has a cost, and a Formula One car might not be right if you're going to be delivering sofas, you want a truck.
Of course. It goes both ways. Again, like I always say this as engineering for good versus good engineering. You don't want to just like, I'm just doing it because good engineering. No, you want to do it for that application. So but
I think the key here is that the conflict solution, there's no one size fits all. We got to have several different, maybe data center categories and several different customer need categories.
Agree.
Yeah, thank you.
All right. Well, we're at the end of the hour. We can keep taking questions if someone has other questions. If somebody needs to drop off, that's fine.
I don't know, like, where did we go with that decision that, like, if someone wants to have questions, but they don't want to be recorded, we can have always at the end of the event, we cut the recording and then you can ask a question.
Yeah. I mean, to echo on that, Ahmad. So IEEE was a little concerned at one point that, hey, when you enter a Q&A stage, don't record that because people might be shy or have concerns about their question going out in the public. My understanding is IEEE is okay with that now. We can record questions. Hopefully everybody's comfortable with that, their question being recorded. But IEEE is okay with that now. We can record questions.
But still, if anyone has that concern, feel free, bring it up.
Let us know.
And we turn off the recording, and then we have those questions. So maybe you should ask it. Any questions? And second, if you want to ask a question but the recording off, let us know.
Yep.
It's like
so Ahmed is saying we are in this IC, we are focused more on applications.
Yes.
So what happened, Ahmed? And since you want to be connected with other standard organizations, currently in IETF, they are looking at two things. Looking at the topology architecture for training models, AI models. And there has been 3 meetings about this. And it's all data center. It is all in the data center. I have to be honest with you, we didn't discuss in any one of these 3 meetings the role of time synchronization. The focus is on the topology architecture, like fat tree, spine and leaf, right? Things of that nature. The second set of meeting, which started in Vancouver, is all about distributed machine learning architecture, where you have AI cluster distributed in multiple data centers. And now, what are the primitives, technologies to support distributed learning and training? So these are 2 applications. Will we study in this IC the role of time synchronization in such a kind of applications?
I see it very like relevant. Yeah, like why not? This is a canvas open, and Hisham, you're part of it anyway. So
Yeah, exactly. So what happened, Ahmed? If there is interest, we can work together with the team on a contribution to one of these meetings in the upcoming IETF, which will be in Dublin. But you don't have to go to Dublin; it's all online.
yes.
And that's the nice
So
thing
it is-
about IETF. Yeah.
Yeah. So and you are in IETF, Rodney, right?
Everybody's in
already-
IETF technically. So yeah, sure.
Yeah. You are in vice chair of a committee in IETF, right?
Yeah.
Yeah.
I have
So-
authored RFCs in IETF. Let's put it that
Yeah.
way. Yeah.
I know what you are doing. So if you are interested, Rod, we can go. Maybe you and Ahmed. Maybe I can join you. Other people can join. You can present our view of what role time synchronization in data center can play in distributed machine learning. Or I'm not sure about the topology. Topology is initiated by the routing group. I think the role of time synchronization in distributed learning, that would be a good contribution.
Yeah. Yeah.
Anyways,
The-
any more questions before? Actually, Hank brought a good point. Like we should perhaps turn off the recording and then ask if anyone has a question.
Yeah.
All right. Any more questions before I turn off the recording? All right, let's turn off the recording and ask that question again.